questions. Okay, so first, let's talk about the exam. So exam 2 is on Wednesday. And the topics are up through, so remember it's all cumulative, so you know there can be questions, there will be questions related to the old stuff, but it's through, not rigid body, sorry, that's a different class, particle kinetics, with pushing and pulling. In other words, particle kinetics up through number 19. The thought process you use up through number 19. Okay, so the next stuff we're going to talk about, we're going to do one more cable pulling problem, but then pretty soon we're going to go on to friction and spring forces, but those won't be on the test. Okay. Mm-hmm. What you should do is just get a Shams outline. Did I mention that to you before? So yeah, if you feel like you need more problems to work on with answers and stuff, so more problems, some with full solutions, some just with answers. Yeah. Yeah, that would be weird if I wrote that and then didn't tell you what it was called. Shams, like a guy named Sham, outline. For physics or calculus-based physics, you know, physics 1, something like that. I don't know exactly what it's called. If you send me an email if you want, I can look it up. And Sham's outlines are awesome. They cost $15. They're paperback. You know, like textbooks cost $200. This costs $15, and it gives little descriptions of how to do things, but it assumes you've had a class that's already described it in detail, and so it just gives you, like, I think each one is like at least 1,000 problems, so you can just work on all the stuff. It's a great way to get ready for standardized tests and stuff. They have it in every one of these for every science class you'll take, you know, so for everything, I would say just buy it for every class you take from now on, you know, $15. A lot of them, you can find PDFs of them for free online, but if too many people do that, then they go out of business and stop making Shams outlines. So maybe like every other one of you should see if you can find a PDF online. Okay, fair. All right, so let's go through some homework questions. Okay, let's go in order because there's probably going to be a few. Yes, 6. That's the lowest so far. Can anyone beat 6? And then additionally, can anybody tell me what 6 is? So you have a circular path, and at the instant that you're considering the object is up at the top, it's in uniform circular motion. What does that mean, uniform? It is accelerating, so be careful with that, but it's not changing speeds. Toward the center, that's right. That's right. So it's not changing speeds. There's no tangential acceleration. Accelerating tells you how quickly velocity is changing. And velocity can change two ways. Its magnitude can change, it's a vector, or its direction can change. So if something's turning, it's accelerating. Zero acceleration is the same thing as a object continuing to move with the same speed in the same direction. So moving in a straight line. So, you know, like when we talk about acceleration, we break it up into the centripetal and the tangential. Toward the center, so it's really not constant, although I know what you're talking about, you know, because the direction toward the center keeps changing. Right. Yeah. Okay, and this object has a mass of 0.2 kilograms. And the circle's center, so I'll say the acceleration of the center is equal to 6 negative 2 meters per second squared. And the object's moving clockwise with an angular velocity of 8 radians per second. And the radius of the circle is 0.4 meters. Is that velocity coming out of the ball like that? No, that's you know, the velocity that where you draw the vector is in meters per second. Yeah, but would that be coming out of the ball sideways? Oh, what would be the direction of this? Like, yeah. That, no, that's the velocity. This is the angular velocity. Two different things, yes. Have that relationship that says the speed of the object is equal to the angular velocity times the radius. So 8 times 0.4 would give you the speed, and then the direction is like this. Squared, yeah. Okay, so all right, and then we want to calculate the acceleration vector. And second, what's the net force? Okay, so for the acceleration, it's rotating this way, clockwise. And so the velocity vector is like this. There's no tangential acceleration because it's uniform. The speed isn't changing. The centripetal is like this. And that is the total acceleration in this case. What? Okay, so all we have to do is figure out the magnitude of this green vector we know that it's in the negative y direction, so then we have our vector, you know? Right, yep. So the magnitude of the centripetal acceleration is omega squared r. So that's 8 squared times 0.4, so 25.6. And what are the units? Yep. Nope, you were right. So the angular acceleration is, oh shoot, can you sign in? Frickin' electronics. Maybe I have everything I need for this one. Thank you. So I have to keep like touching this every 20 seconds. So 25.6 meters per second squared. From the drawing, we can see that it's in the negative y direction. So the centripetal acceleration vector is 0, negative 25.6. Or you can write that as negative 25.6 j. Those mean the same thing. And then that's also equal to the total acceleration because there's no tangential part. Any questions about that? That's right, for B. Yep, so F net is just 0.2 times 0, negative 25.6. Which is 5.12 newtons, or you can write that as negative 5.12 J. Yep. Oh, yes, I've skipped that part. Yeah, so in this problem, so usually in these circular motion problems, the center is fixed, but in this one, the center has an acceleration. Yeah. So those are just stops along the way to finding the answer. Wrong. Okay, so this is if the, okay, so this answer is the acceleration of particle, assuming that the center is fixed. So the answer for the acceleration would be if the center isn't moving. The center is moving, so now we have to use this. The acceleration of the particle relative to the ground is equal to the acceleration of the particle relative to the center plus the acceleration of the center relative to the ground. So the acceleration of the particle relative to the ground is 0, negative 25.6. Plus what we were given for the acceleration of the center, 6, negative 2. And so that's 6, negative 27.6 meters per second squared. And now for part B, so first, we can think of this as we've calculated two different accelerations for that particle for that particle p. We calculated an acceleration given that the center is fixed, and we've calculated an acceleration in the ground coordinate system. Which one of those do we want to use for Newton's second law? And why is that? That's right. Yeah, that's right. Newton's second law says F net is equal to the mass times the acceleration for an acceleration calculated in an inertial coordinate system. That means the coordinate system can't be accelerating. So if your coordinate system is fixed to the center and the center is accelerating, Newton's second law isn't going to work. Who's with me on that? Okay, so F net is equal to 0.2 times 6, negative 27.6. That's 1.2 and negative 55.2 newtons. Yes? Okay. Mm-hmm. Yeah, I mean, if... Yeah. Okay, so if it asks you for anything that's a vector quantity, just give it in the vector form. Velocity, acceleration, force, those are all vectors, so give it as a vector, unless it specifically asks for the magnitude. Any other questions about that one? Okay, other ones you want to see?
Yeah, for 7, that one's fixed. 7.
The center is fixed, yeah. Is that what you mean?
Yeah.
Yep.
Do you have the, instead of going through that one, do you just give the answer?
Nope, I don't.
It would just be the 15 times 15 squared times the radius of the tube, right?
I don't know. Let's go through it.
That's a good.
Thanks.
I really like it.
Okay. Is it at the top?
Yeah, it's at the top.
Okay, so this guy's doing a loop-de-loop. So the way I drew it, he's going this way. And the circle has a radius of 2 meters. For what? And that's a radius, not a diameter, so it's 12 feet tall. Yeah. Yes? Okay. That's how I would do it. You can use any coordinate system you want, though. But no, we're looking sideways at him, and he's going up and over doing a... Does anyone want Henry to come up and explain that's what motorcycles do and do not usually do? Okay, you sit down. Okay. And what do we know about this? The speed is not changing at the top. So that's right. So for this instant, we're going to treat it as uniform uniform circular motion. And the speed is 15 meters per second. Okay, I'm going to switch over to just a simpler drawing of circular motion. So there's the person. It's rotating this way around the circle. So we'll go back to this before he has to get out. Let's go. Okay. So velocity vector is this way, and we know it has a magnitude of 15 meters per second. There's no tangential acceleration because the speed is constant just at this instant. That doesn't mean that over the whole circular path, the speed is constant, just at that instant. But that's all we're calculating here. There's a centripetal acceleration like this. And because it's uniform circular motion at this instant, that's the total acceleration. The total acceleration vector of the object at this instant is just the centripetal acceleration. And there's two ways to calculate the centripetal acceleration. This is omega squared r, or you can also calculate it as the speed squared divided by r. So 15 squared divided by 2 is 112.5. It just is the magnitude, and then the vector that means that's meters per second squared. So the centripetal acceleration is, again, the way I have it drawn, this is in the negative y direction, just like it was in the last problem. So that's 0, negative 112.5 meters per second squared, or negative 112.5 J. And that's the total acceleration. In this case, the center isn't accelerating. This would be a different answer if the loop-de-loop was on a truck that was accelerating or something. The net force at this instant F net is equal to the mass, and the mass is 350 kilograms times the acceleration, 0, negative 112.5. Can someone multiply that? 39,000? 375. Okay. That's a lot of force. Okay, that's the net force. Okay, thanks. Okay. A is easy.
The radius is, or the circumference of the circle is 4 pi, right? Of the lagoon.
Yes.
So wouldn't that make like 7.5 radians per second? Not 15. Because 15.
Oh, well, you can use either one of these two formulas. He's going 15 meters per second. That's a speed. Right. Right. You have to calculate omega. It's not W, it's omega. So let's see. So to go from, so if we wanted to calculate omega, we would use the fact that the speed is equal to omega times r. Okay. So we got that F net, but now the question is, this is the total force when you add up all the forces. That F net is made up of two separate forces. One is the weight, and the other one is the force applied to the motorcycle by the path. Okay, so let's draw a free body diagram of the motorcycle. Okay, the motorcycle upside down. And what forces are acting? There's a downward force of 350 times 9.81. And then there's a pushing contact from the surface on the wheels. I'll call that the normal force. And we're trying to find the normal force. That's the force that's applied to the motorcycle by the surface. And Newton's second law then says 0, what's 350 times 9.81? Negative 3,433.5. And then plus 0 negative n is equal to the mass times the acceleration that we calculated, 0 negative 112. And so if you use the y equation, you get n is equal to 350 times 112.5. And that was positive 39,375 minus 3,433.5. And so the normal force is, what's that if you subtract? $35,941.5 newtons. And it's pointing down, or you could write that as 0 negative 35,941.
What is that?
That's the speed. That's the magnitude of the velocity vector. Yeah.
So you just divide by.
For what?
For maybe a little listening. I read that v squared over r. We could just do it that way, right?
Yep.
That's fine.
That gives you the acceleration.
Okay.
The net force. And then for the last part, we, instead of writing it instead of just calculating the net force, we broke it up into the two individual forces. One of those forces is the weight, and the other one is the pushing contact from the ground. Well, we do it. We started with a free body diagram, the same way we always do it. Apply the weight force, and then look around the boundary for a contact, and the only contact is with the surface, and it's a pushing contact. And then we can calculate that in. Yep. That is a mass of 350 times 9.81. That's the weight force. Okay, so that's a lot of force. And so, like, if you work for Barnum and Bailey or whatever, like, you got to take that calculation into account when you calculations like that into account when you figure out how big the path is or how strong the path is going to be. Yeah, that's I guess as long as. Okay, so that's a good question. Let's do that. So how fast does this guy need to go before he falls off at the top? If you're not going fast enough. Yeah, that's perfect. Yep. Yeah, he's going way too fast. Yep.
Where 1/2 x squared is greater than or equal to.
Yeah, so let's figure out what's the slowest he can be at the top to stay on. And yeah, you thought of it just right. Like, as long as there is 1 Newton of force pushing against the wheel at the top. Right. So we'll use 0 as the cutoff, and so the speed is v. What? Yeah. He gets paid well. So now the motion's going to look like this. The speed is going that way. The centripetal acceleration is this way. The magnitude of the centripetal acceleration is v squared over r. What was the r? 2? And so the total acceleration is 0. Write that as negative 0.5 v squared. Okay. Now do a free body diagram of the motorcycle. There's a weight force down of 3433.5. Right. Yep. And then our cutoff between staying on and not staying on is there's a normal force that's equal to 0. Okay. So in other words, this vector isn't there at the cutoff. Yeah, exactly. So he would stay on that circular path even if the ramp disappeared at that location.
Right? That would have to counteract the force of, like, him pushing into the ground would have to be equal to the force of the ground pulling down on him.
Well, so what it really is, F net is equal to the mass times the acceleration. The acceleration is what's required to stay in that circular path. And now we're assuming that normal force isn't contributing. The question is, how fast does he have to be going for the weight to exactly provide the centripetal acceleration? That's right. So 0, negative 3433.5 plus, this 0 normal force is equal to 350 times 0, negative 0.5 v squared. And so the y equation says negative 3433.5 is equal to negative 350 times 0.5 v squared. And so you can write that as negative 9, divide both sides by 350, negative 9.81 is equal to negative 0.5 v squared. 19.62 then is equal to v squared. And so v is equal to 4.43 meters per second. At the top, he needs to be going, that's almost exactly 10 miles per hour. So he needs to be going exactly 10 miles per hour right at the top. Yeah. At the top, because he's slowing down the whole way, and that's the slowest he's ever going to be. Right. Yep. Right. Any other questions about that one? Kevin, could you let me back in here again? This is good exercise. Thanks. Okay, what's the next one?
Which one?
Okay, let's do 8. 8. Yeah. Yeah, 8's pretty quick. I mean, so. Okay, so you got this car. And inside the car, there's a coffee cup in free fall. Yeah. You have a cool car, Meredith. So the acceleration of the car relative to the ground is, if I use this coordinate system, it's negative 4, 0. And what we know is the acceleration of, the cup in the car, and car and coffee all start with C. So this is the acceleration of the car relative to the ground. What's the acceleration of the cup relative to the ground? That's right. So acceleration of the cup relative to the ground is 0, negative 9.81. Because the cup's in free fall. And so the first question is, what's the acceleration of the cup that's observed inside the car. So we'll set that up as a relative motion equation. Acceleration of the cup relative to the ground is the acceleration of the cup relative to the car plus the acceleration of the car relative to the ground. So we have 0, negative 9.81 is equal to cup relative to the car, that's what we're trying to find, plus car relative to ground is negative 4.0. So add this vector negative 4.0 to both sides, and you get that the acceleration of the cup relative to the car is positive 4, negative 9.81. Yep. No, because we went through the algebra of this. Like this was the relative motion equation, and we solved for this one, so we had to move this to the other side. And so it's just algebra, but what that says is the car is, so imagine the car bumping into something. What happens right at that instant of impact? If you have a coffee cup sitting on your dashboard and you run into something forward, the car accelerates backwards really quickly. Okay?
This is set up wrong then, right? This cup relative to car would be 0.
My drawing is backwards is what it is.
Well, like the cup relative to the car would just be negative 9.81 because the car's moving at the same speed as the cup. Accelerate now. It's falling straight down. Yeah, so the cup relative to the car would be 0 to negative 9.1.
Because
the cup relative to
It's relative to the ground that's always 0, negative 9.81.
But the car's moving
it's the velocity of the car, and it's like when the cup falls,
It's accelerating.
So an observer on the ground always, something in free fall, always has an acceleration downwards of 9.81 to an observer that's on the ground. So someone watching this happen is like, that cup's in free fall.
But it would also look like it was, like we saw on the bus, it would also look from outside the car like it was shooting backwards at 4 meters per second.
No, it would look like it's shooting forward if you're accelerating backwards. So here, think of this case, okay?
Oh, I see what you mean. Like, it was,
If it's going forward and crashes into something, okay, its velocity is still forwards, but its acceleration is backwards, and that's what we're talking about here. And if you crash into something and your cup is sitting on the console, where does the cup go? Forward. Yep, forward.
Okay.
And so an observer in the car thinks that the coffee goes flying towards the windshield. Well, you know, that's why when people get in bad crashes, they go through the windshield. So, but really the way to do this problem is to do the algebra, not to, your intuition you can use as sort of a sanity check, but the way to do it is do the algebra, and then we got a positive 4, so it's going forward, Okay, just set it backwards, yeah. And then, so we have 2 accelerations for the cup. Cup relative to ground is 0, negative 9.81. Cup relative to car is 4, negative 9.81. Which of those 2 can we use in Newton's second law? Ground, yep. So for part C, the acceleration of the cup relative to the ground is the one that's in an inertial coordinate system. So that's 0, negative 9.81. And then Newton's second law says calculate the net force. That's true, but we can just put it in as m. So F net is equal to 0, negative 9.81 m. So does that make sense that that's the net force? Yeah, because it's in free fall, the only force is gravity, and that's mg down. Yes? Part A. Positive 4, negative 9.81. That's the acceleration of the cup relative to the car. B. I'm sorry. A is an observer outside the car. So that's acceleration of the cup relative to ground, and that's 0, negative 9.81. To the observer inside the car, it's 4, negative 9.81. That's to the person. So an observer, so if something goes through the windshield, here's what it looks like to different observers. To an observer on the ground, the person just becomes a projectile. The person has a high initial velocity and gets launched through the windshield. Nothing looks weird. I mean, nothing looks weird about the physics of that, To an observer inside the car, the physics look weird. It looks like the person all of a sudden accelerates forward. Okay. Okay, what's the next one?
Let's do 9 to that one about first.
9 is one where you get a force function. So I don't know if that's the one you're thinking of.
That's one with 3 parts, right?
Okay.
Oh yeah, then don't do 9.
Okay, 9. So this one, when time is equal to 0, the velocity vector, the position vector, and the velocity vector are both 0. And then the net force vector as a function of time is t negative 3t. So what's the object's position vector as a function of time? All right, well, Newton's second law says F net, so t negative 3t, is equal to the mass times the acceleration vector. And so the acceleration vector as a function of time is t over m for x, negative 3t over m for y. And we know that the acceleration vector as a function of time is the time derivative of the velocity vector as a function of time. Right? So we can write this as the x component of the velocity time derivative is equal to t over m, and the y component is equal to negative 3t over m. Integrate both sides, and you get that x component of velocity Yeah, we want to integrate both sides. So we get that the x component of velocity is p squared over 2m plus a constant. Well, the constant ends up being 0 because of our boundary conditions. The y component of velocity is negative 3 p squared over 2m. Both of these constants are 0, so there's the function. And then you just have to integrate again to get the position function. Any questions about that one? So that one's just to use Newton's second law to calculate the acceleration function, then it's just 2 integrations to get the position function. Just remember that you always have to deal with those constants of integration. Okay. All right, let's take a 10-minute break. Come back at 5 minutes to 9, and we'll keep going.
You know what this teaches you about economics? Supply and demand. Something that you will never understand. I do not. My size is so small, she can only do 20 pounds. How big is your size? We don't get it right. Wait, oh my gosh, yes.
So did anyone who is scheduled to go want to go? Yeah, I read like smaller ones. Did you like hand out a
We're all going to be safe once we have our guns, Meredith.
Yeah.
Friendly fire.
Can you imagine how much police are looking forward to getting to a building where there's 100 agitated people. Yeah. It's so ridiculous.
There was an armed security guard at the school.
Yeah. Yeah, so we just have to be like better than him. Yeah, right.
Got shot by the guy. This was train people slightly better than him.
Yeah, exactly.
It's also the same people who want to sell.
I'll 3D print us guns, Meredith.
No, thank you. I don't want a gun.
I'll hold yours. I need double. I'm gonna teach like this.
Hey guys, can you do your homework?
High noon.
The bell doesn't just switch to what I do.
Yeah.
About myself? On someone else? Oh, hours? Yeah. You forced to do homework. Like, I don't want to do homework. My God's like, do homework. Takes down your phone every second. That's what you want to do for the rest of your life. Landon, you know Arden? Yeah. What he said. Arden said to his girlfriend, he's like, isn't she beautiful? She's so pretty. And I was touched thoroughly and very
You just had to say
Okay. So now you want to do the one with the 3 carts? Number 11? Okay. Yeah. Skipping 10. 11's the harder one with carts. 10 is the one with the thing hanging in the elevator. Okay.
So basically the way to remember this is the first cart is being pulled. The last cart is being pulled by all the other carts.
Well, this one they're all being pushed.
Okay.
So
The cart closest to the push has nothing to get back, right? But like the cart farthest away from the push is the hardest move because there's the other carts behind it.
I don't know. I would say the way to think about this is just to think about the steps of doing it and just solve it. You know what I mean? Like, there's no need to really do too much thinking about it. Just get these steps down. So this one's 10 kilograms on the left, 5 kilograms in the middle, and 8 kilograms on the right. And then there's a 50 Newton force on the right. So what's the acceleration of the 3 carts? So at the beginning, at the beginning, are you guys ready? On these problems, whether it asks you for the acceleration of the carts or not, that's the first step. You have to calculate the acceleration. Okay, so we're going to do a free body diagram of all of the carts together. This level of detail is probably unnecessary, but whatever, there's the outline. So what forces are acting? There's a downward weight force. That's 23, the whole thing has a mass of 23 kilograms, so 23 times G. And then go around the boundary and look for where the surroundings make contact. There's a pushing force from the ground. I'll call that N total. There's a 50 Newton force over here. And then there's no other contact with the boundary. So that's it. And then Newton's second law, I'm just going to use the X equation. We have a force of negative 50, and then that's equal to the mass times the acceleration in the x direction. We'll just call that A. We know the only acceleration is in the x direction because it's parallel to the ground. And so A is equal to negative 50 over 23. What do you get for that? Negative 2.17 meters per second squared. And so the acceleration vector is that in the x direction and 0 in the y direction. Any questions about that? Okay, so now we want the force vector applied to the 10 kilogram cart by the 5 kilogram cart. So now we're going to isolate the 10 kilogram cart. That's the one all the way on the left. There's a downward force of, now our isolated body has a mass of 10 kilograms, so 10 G acting down. There's a pushing contact from the ground, I'll call that N10. And then where else along this boundary is there contact with the surroundings? On the right, that's pushing contact from the other one. And so since it's pushing, it's perpendicular to the surface toward the chosen body. I'll call that R. And there's no other contact. So now Newton's second law, I'll just use the X equation again because that contact force doesn't have any Y component. We have negative R is equal to the mass of 10 times the acceleration of negative 2.17. And so R is equal to 21.7 newtons. It's acting in the negative x direction, so if you wanted this as a vector, that force vector on the 10 by the 5 is negative 21.70. Any questions about that one? Okay, so now what's the force vector on the 5 by the 10? All right, so what are we going to isolate this time? If we isolated, the first thought is you'd want to isolate that middle cart, the 5 kilogram cart. But if you do that, you'll see that you have too many unknowns. So let's isolate the two parts on the right as a single thing. So free body diagram of the 5 and the 8. There's a downward weight force. The total mass is 13, so 13g. And then there's a normal force. I'll call that N58. That's not going to come into this problem. All we have to know is that's different than any of the other normal forces we've used. And then where else is there contact with the surroundings in this boundary? The force over here, it's pushing, so it's not a cable, but there's, that's right. So there's the 50 Newton force here, and then on the other side, there's this force, I don't know, I'll call it R2. And Newton's second law, the X equation again says R2 minus 50 is equal to the mass, 13, times the acceleration of negative 2.17. And so R2 is equal to 50 minus 13 times 2.17. And what do you get for that? You should get positive 21.7. And so the force on the 5 by the 10 is positive 21.70. Okay, so notice this interesting development. This force here, the force on the 5 by the 10, is exactly equal and opposite to the force on the 10 by the 5. That's a super weird coincidence, right? It's not a coincidence. So we haven't talked about it yet, but one of the important principles that's going to come up is Newton's third law that says if you have a contact force between two bodies, the force that contact applies to one is equal and opposite to the force it applies to two. That's the thing that says for every action there's an equal and opposite reaction, but we'll do it in a more sort of mathematical way than that. So you look at this and you're like, what the? That's you. What the? You're probably like, Charlie, come check this out. And he's just like, that's probably just a coincidence. You're like, I don't know. Yeah, that's like your catchphrase now. Oh no, I got it back. I did it quickly enough. Yeah. Wow. Okay, and then yeah, and then that's basically what D says to do. Compare the answers to B and C. Something fishy's going on here. Yes. Mm-hmm. Oh yeah, well we haven't talked about Newton's third law yet, have we? I didn't think so. So the way I did it without using Newton's third law is I isolated the 5 and the 8 together. And then I just calculated that pushing contact. And when I calculated it, I got that Newton's third law.
For like our Newton's third law work, do we have to like include that when we're putting thing, or can we just
Say it again, the normal? Yes, put in all the forces in your free body diagrams. You'll be happy later that you got that habit. If you don't draw the free body diagrams, don't even. Just don't even. Just pack up your stuff and go home and watch cartoons. Anytime you use Newton's second law, draw a free body diagram. Yeah. Okay. Any other questions about this one? Okay, what's the next one?
117. No, let's do what, the elevator.
With a card on another card?
Yeah.
Oh, your team was kind of tough.
Oh, you're right. Yeah, I meant 12.
The one with the elevator?
Mm-hmm.
Okay, so we have a 4 kilogram cart on the bottom and a 1 kilogram cart sitting on top. It is dangerous. And let's just do one where the elevator's accelerating. These questions are pretty similar. If it's not accelerating, if it's moving with a constant velocity or stopped, then it's just like it's not in an elevator at all. The acceleration is 0. These are just sitting there. So let's do one where it's accelerating upwards at 1 meter per second squared. What's the force vector the elevator applies to the 4 kilogram cart?
So well, he said it's the 4 kilogram and the 1's on top. Put that in.
Yeah, we'll isolate the 2 together. That's right. So free body diagram of both. Right. Oh, don't do that. Because, that'll let you get through the simple problems, but you won't have the habits for when you get to the harder problems. Okay, so this is both of them. The total mass is 5 kilograms, so 49.05 down. And now go around the boundary looking for contact, and the only contact is that normal force, the pushing contact from the elevator to the lower cart. And then Newton's second law. Let's only use the y equation because nothing's going on in the x direction. So we have 49.05 in the negative y direction plus n is equal to the mass of 5 kilograms times the acceleration, which in this case is positive 1, and so n is equal to 49.05 plus 5, so 54.05 newtons. And so the force on the floor by the elevator is, since this n is in the positive y direction, 0, positive 54.05. So that's in there because I isolated both of these two together. Okay. If I would have isolated only the 4, then you wouldn't have to include that in there. But there would be a contact force from the one above that would give you too many unknowns to solve by itself. So then you'd have to isolate the 1, you calculate that contact force, and in the end it would all end up the same. The easiest way to do it is just to isolate both together. Yeah. Yes. So if I would have done it with all the vectors in there, it would have been 0, negative 49.05 plus 0n is equal to the mass times the acceleration of 0, 1. And then from there you see that the x equation is just 0 equals 0, so that doesn't help you. And then the y equation says what I had up there. Any other questions about that one? Okay, what's the next one? Oh, that's funny. That one's so easy, actually, but it looks really complicated. You don't. No, when you... Yeah, I got mine when I was 13. When I was 13, I was still trying to figure out what my favorite flavor of paste was. Okay, so we have this 150 kilogram mass, and okay, so it's a setup like this, and it looks complicated. And it doesn't give you a lot of information about locations and stuff, which seems like you need all that stuff. The only thing it gives you is the angle here and the angle here. Okay, so free body diagram of this weight. So you just have to be systematic about looking for the forces. What forces are there? There's a weight. That's 150 times 9.81. So 1471.5. And then where is their contact with the surroundings? Yep, just here and here. And that's the same cable, just going through pulleys. So the magnitude of those forces are the same. And we know these angles. And if you get to this point, that problem looks a lot easier than it did in the drawing. You know, I could have made that drawing 50 more pulleys or whatever. You know what I mean? And it would have looked like I'm not even going to try to do that, but the free body diagram would look the same. So anyways, the idea of this problem, really, the main idea of this problem is don't get hung up on the picture. Just go through the steps, you know? The steps will get you there, you know what I mean? So the last thing we have to do is figure out the components of these force vectors. Okay, so first let's figure out the components of the force vector on the right. Okay, that's like this, where this angle is 40 degrees. So what's the counterclockwise angle from the x-axis to? Right, that one's easy. Okay, so that force vector is t times cosine of 40. T times sine of 40. And now let's think about that other force. It's like this. In one component they will, and in the other one they will add. Right. Right. Yep. Okay, so this angle is 40 degrees for the second one. So what's the counterclockwise angle from the x-axis here? 140, yep. So F1, F2. This one is t times cosine of 140. T is the magnitude of that tension force. So F1 then is 0.642 T, no, 0.766 T. 0.64, I think maybe it's 3 T. And this F2 is negative 0.766 T, positive 0.643 T. So now Newton's second law says 0.766 T, 0.643 T, plus negative 0.766 T, 0.643 T, is equal to the mass of the thing times its acceleration, but it's just hanging there, so that all comes out to be 0. Oh, and I forgot the weight. No, it will matter. So this is 0, negative 1471.5. So now the x equation, like you said, those two cancel out and you just get 0 equals 0. So that doesn't help. But the y equation says, now, you know, notice the two y components add. So you get 1.286 T is equal to positive 1471.5. And so T is equal to, what's that, 1144?
Yeah.
Okay, 1144.25 newtons. And so then the force vectors, if it asks for the vectors, plug that back into these force vectors you calculated before in terms of t, and you get those, you get the components. 1144.25. So that one, if you let your fight or flight response kick in looking at the problem, then nothing happens. But if you look at it and you think, I'm going to start with a free body diagram and then write in what I know about the forces, what I know about cables and whatever, it ends up being the easiest one to calculate in this whole thing, you know?
Basically, that's the steps.
Right. Yes, exactly. It's those steps for everyone, and then beyond that, you're just you just have to differentiate between the pushing forces and the pulling forces to get the directions right, you know. Want to do another one since we only have 8 minutes left? Oh, 19 is the last one. Yeah, so we can go 16. Okay, so this is an elevator again. And inside the elevator, you have 2 boxes hanging, 4 kilograms and then 3 kilograms. And the elevator is moving with a constant velocity on this one. So remember, constant velocity means 0 acceleration. Okay, so let's say we want to calculate the So first, what's the force vector the top cable applies to the 4 kilogram? So a free body diagram of both of these. Okay. So there's a weight force. The total mass is 7 kilograms. So the weight force is 7 times g. And then the only place the surroundings make contact with the boundary is the pulling force at the top. I'll call that T. Because if I isolated just the 4 kilogram, we would have a weight force, and then we'd have T1 like this, and T2 like this, and we'd have a single equation with 2 unknowns, and we wouldn't be able to solve it. So we want to choose to isolate bodies in a way that gives us only 1 unknown. Okay, so Newton's second law, the y equation says negative 7g, which is 68.67 plus T1 is equal to the mass times the acceleration. That's 0 because this has a constant velocity. And so T1 is equal to 68.67. So now let's, for part B, we'll calculate the force, the middle cable applies to the top box. Well, now I'll isolate the top box. Mm-hmm. Okay, so this time we have. That's fine. Yep, you can do it that way. This is fine too because now we know that this force is 68.67. We just calculated that. And then we'll call this T2. And so Newton's second law says, in the y direction, says 68.67 minus 39.24 minus T2 is equal to 0. So T2 is equal to 29.43 newtons.
And for the last problem, is it only A and B? Or is there a C?
There's a C. What's the force vector the middle cable applies to the 3 kilogram? So this is 29.43 down.
Yeah. So
That's right.
we can do that, right?
That's right, because this time, you know that's true because a single cable applies the same force to anything.
Otherwise, we're like,
Yeah, right. That's right. Any other questions about that one? Okay, test Wednesday, so make sure you're good with this stuff.
What are we doing on Friday?
Lecture.
Oh. And then we have spring break next week?
Yeah.
Professor,
Yes.
you know